All right, these are the notes for Unit 1, Day 3, and they start on page 9 of your packet. And so yesterday we talked about tables and graphs and approximation or estimation and plug and shove, direct substitution. So now we're looking at limits of indeterminate forms and manipulation techniques. So this is a different technique because we have a different situation. So I'll get into what an indeterminate form is in just a second. But our central question is, why are manipulation techniques necessary? Why can't we just always plug and chug? Okay, so that's kind of the secondary sort of question. Okay, so first, before we get into the nuts and bolts here for these notes, I just want to make a quick comment about fractions. Okay, because we're going to look at a lot of fractions or a lot of rational expressions, right? This is a fraction, but we also call it a rational expression, and so we need to discuss what happens in these four scenarios here. Okay, so because it'll help us evaluate limits. So for instance, let's look at these four things as fractions. Okay, because it's a number over a number, right? And that's what a fraction is. So 1 divided by 1,000,000 is 1 divided by a really big number. Okay, when we take 1 and divide it by a really big number, we get tiny pieces, right? So this is basically, we can approximate that as to be 0. Likewise, 1 divided by 0 is taking 1 and dividing it by nothing, okay? And that we know is undefined, is infinite, excuse me. That will lead to a really big number. And then 0 divided by any number, 0 divided by 7, 0 divided by 20, 0 divided by 1,000,000, right? That is 0. And any number divided by 0, again, is like this. This is any number, right? 1 is a number. That's infinity. So these four rational expressions, now I'm going to use that fancy term, rational expression. Those four rational expressions, we can determine the value of. So these are not indeterminate. We can find values. So indeterminate means we don't quite know what's happening with the value. And that happens when we get an expression, a rational expression that is 0 over 0. We're not quite sure. Is it 0? Is it infinity? Is it something in between? We're not quite sure. And that's why we need these manipulation techniques, is we need to take this and get it into a different form so that we know what's happening from a value standpoint, okay? So 0 over 0 is indeterminate. Means it tells us that something else has to be done, that we have to engage in some other manipulation. Okay, so let's take a look at this. We know what this looks like. Remember I said this sign of x over x is really important to know what it looks like. And I'm drawing it in the air, and I know you can't see me, but I'll make the sound when I draw it, right? It goes, right? And so it's got that big hump in the middle, and then it's got little hills and valleys, and they get smaller and smaller as you go up. Okay, well, think about plugging in 0. Sine of x, sine of 0 is 0. If we put 0 in for x, we have 0, right? If we plug in 0, we get 0 over 0. Oops, 0 over 0 here. Okay, we get 0 over 0. So we need another strategy. That's why we graphed it, so we can look at the picture. We need another strategy to evaluate it. We just can't plug in a number. We can't do that option B on the flow chart where we just plug in and get a numeric answer. Okay, we need another strategy. And our strategy for the previous class was to graph it. But we're not always going to be able to graph things. We're going to have manipulative strategies that we can do analytically that don't involve graphing. So let's take a look at this. So what is happening at -2? I've got a rational expression. I'm using the fancy term again, rational expression, right? A fraction. But the reason why we call this a rational expression is because we have a function over a function. Okay, that's why we call it a rational expression. So I'm going to start by graphing this. Okay, and then we're going to transition from graphing to manipulation so that we can do problems like this without graphing. All right, so what do you know about denominators when they're 0? Think about that. When the denominator is 0, there's something shows up on the graph. So take a second, pause the video, think about that. I'll give you the answer in a second. Okay, we know that when the denominator is 0, we have an asymptote, right? Vertical asymptote. We learned that in previous classes. So let's graph this. I'm going to actually physically graph it here on my TI my TI 84 plus CE. Okay, and let's see, do I have anything graphed here? I don't think I do. Come on. Oh, not quite sure why it's not functioning. Okay, so I have to figure out why this is not functioning. Give me just a second here to figure that out. Okay, figured it out. It's a miracle when I can get through these notes without something getting screwed up here. Okay, so let's graph this. Now, this is the tricky thing about graphing. We know, let's get this here so I can see it. We're going to graph this, and it's a rational expression. So I have rational expressions are like grouping symbols. We have the top and the bottom, and the top is its own group, and the bottom is its own group. And so the way we have to graph these things in our graphing calculators, we have to use the parentheses. So we can group everything in the top. So x squared plus, oops, I gotta switch this up now, plus 5x plus, I believe, plus 6. That's all grouped in the top. Now I can hit my divide, and I can group in the bottom, because we got to divide by that whole thing, x plus 2. So we're going to expect to see an asymptote at -2, right? This is the limit as x approaches -2. And if I put -2 here, I get 0. So we think we have a vertical asymptote, right? Because that's what we learned in previous classes. Well, let's graph this. Oh my gosh, I don't have a vertical asymptote. And there's a specific reason why. But we know that when we stick -2 here, we get 0. So what's happening at -2? Here's -2, right? We would typically see an asymptote here, but we don't. What is happening at -2 here? Okay, that we don't have an asymptote. And the story is really what's happening in the numerator. Look at the table. And look at the table here at -2. I got to arrow up a little bit. -2 says error. Okay, and the reason why it's saying that is because when I plug in -2 in the top, I also get 0. Okay, so that's getting in my way of my calculator being able to accurately represent the limit. Okay, now graphically, I can estimate the limit just by looking at the graph. Where we'll be trending as we approach -2 here, what y value are we trending to? Okay, we're going to see that analytically too. Okay, so with direct substitution, like I said, if I put in -2, I get 0/0. This is my indeterminate form. So I'll grab enough battery. Wait, I'll talk faster than I typically do, which is very fast. So 0/0, that's the red flag that says I need to engage in other manipulation techniques to simplify this expression to get rid of this 0/0 scenario. Okay, so we plug in, we get 0/0. We're looking at the strategy. Graphically, this is a kind of a zoomed in picture of what I just showed you. Here's -2. It looks like the limit should be 1, right? Because this is the y value, and it looks like it's trending towards 1 from the left and the right. And if we were presenting this as a graphical problem, that's what the answer would be. And that is the answer. Okay, so why no asymptote? The denominator is 0, but the numerator is 0 too. And that takes the asymptote away. What it actually creates right there is a hole in the graph. There is no finite value at -2. There's no function value. But if you look at this, we can treat this as a table, just like the previous class. This is approaching 1 from the smaller values, and this is approaching 1 from the bigger values. And so since we're approaching 1 from both sides, that's the limit. Okay? So how do we approach this with a manipulation technique? How do we, in other words, this is approaching it graphically, this is approaching it tabularly. Okay, how do we approach this analytically? Analytically means we're going to do some manipulation, some algebraic or some manipulation using functions. Okay, so that's the hole here, and that's the indication that there's a hole here. We've got this error in our table. Okay, so pulling out this, going back to this flow chart, we got to realize that this we've already talked about, right? We've talked about plug and chug and getting a finite value, and that's also the limit. We did that in the previous class, in the previous notes. And we did this too, the tables and graphs. We're not talking about that part of the flow chart anymore. We're talking about this part, part D, the 0 over 0 in scenario. When we look at, and if you notice, this is almost exclusively rational expressions, right? This is what we do for rational expressions. And just a caveat here, this is also true for infinity over infinity. We won't run into this too much though, but we will in a later chapter. So this is what we're talking about today, confirming the indeterminate forms. D, option D, indeterminate. We have to re-express. So following the flow chart here, following the flow chart. Hold on here. I'm going to pause the video one more time so I can plug in. Okay, I'm back. If we have to re-express it, if we follow the flow chart here, these are the options for re-expressing. We can factor or expand. We can use trig identities to rewrite either the numerator or the denominator or both. Or we can use conjugates. I'll get into what a conjugate is in just a second, a little bit later in the notes. So these are the options we have. So looking at this expression, going back to our options here, there's no trig involved in this, so that's out. I'll just tell you right now, there's no conjugates involved. I'll show you what that looks like in a second. So that's out. So we're left with this option. Can I factor the top or the bottom or both? Can I expand the top or the bottom or both? And looking at this, it looks like I can factor the top. And that's exactly what we're going to do. So when we factor this, you can do your star method, or you can just think of what multiplies to 6 and adds to 5. Okay, when we factor these things, when we factor this quadratic, we factor into x plus 2 and x plus 3. Look at what happens. Look at the top, look at the bottom. There's something obvious there, right? What can we do to simplify? Think about that for a second. I'll tell you in a second. Okay, I'm going to tell you now. We can cancel those, right? Those are like factors. X plus 2 and x plus 2. Those are canceled because those are like factors. And now we've re-expressed, right? It was this, it's now this. We've re-expressed this as x plus 3. And if you notice, whoops, wrong screen. If you notice, x plus 3 is a line with an intercept at 3 and a slope of 1, right? Up 1, right 1, up 1, right 1. Isn't that what we see? We see a line here, but because it came from a rational expression, we have a line with a hole right there. Okay? So that's because, and the hole is created by the fact that we're canceling factors. Okay, now we can plug in -2. That's the cool thing. The denominator is gone. The problem is gone. Right? That was always the kind of the stick in the mud there is we plugged in -2 and that was 0 over 0. But the fraction is gone. So now we can plug in -2. -2 plus 3 is 1. There is an analytical answer to this problem. The limit is 1. So that is an example of re-expressing using factoring. Okay? We canceled factors, and then we were able to just go back and use that substitution. All right, here is another indeterminate formula. I plug in 0 for h. I get x squared minus x squared, which is 0. And I get 0 and about 0 over 0. Okay, so I've confirmed this. Notice I'm always displaying that I get 0 over 0 and it's indeterminate. I'm going to expand this. X plus h quantity squared. I'm going to FOIL this out, right? It's going to be x squared plus 2xh plus h squared. So I'm going to do that. Minus x squared, right? Because that's right there over h. Okay, so what can I do for simplifying? Look at this. This and this go away. They're opposites. So now I'm down to this. Sweet. We're actually going to use this technique at the end of the unit a lot. Expand and cancel. So now I have this. And you might think, well, gee, if I plug in 0 here, I'd still get 0 over 0, don't I? And I do. So that means I have to still re-express this. Now the bottom you can't re-express, it's just h. But let's take a look at what we can do with the top here. So think about this. Pause the video. What can I do with the top? I'll tell you in a second. All right, I'm going to tell you now. So we're going to go back to those techniques. We expanded. Now we're going to factor out an h, right? I see an h here, and there's an h here. Couple of them. So I'm going to factor out an h, and h times the quantity to x plus h. Why does that work? Because look what happens when I start to express the numerator as factors, I start to be able to cancel out the denominator. So again, I can cancel out the h over h. There's a whole location h, whatever that is. And now I've re-expressed it, right? And since the fraction is gone, the 0 over 0 scenario is gone. Now I can plug in 0 for h, and that goes away. And so my limit is 2x. Notice this limit. It's not a number. It's 2x. It's 2 times whatever x is. If I put 7 and 7 here, then this would be 14. If I put 10 and 10 here, then this would be 20. If I put -2 and -2 here, then this would be -4. So in this case, this limit is an algebraic limit, and that's okay. Sometimes that happens. Okay, so going back to that flow chart, we see we're starting to see some trig functions, right? So we know that this is going to be a trigonometric manipulation. So this is where your trig flip comes in handy. The top, we can't really express sine of x. I mean, it's just sine of x. There's really no convenient way to re-express it, but we can re-express tan of x, right? We can say tan is sine over cosine. I noticed I didn't do something here. I should have put pi in here and pi in here. Because sine of pi is 0, 4 times 0 is 0. Tan of pi is 0, I have 0 over 0. I didn't confirm that, and I apologize for not doing that. You should do that each and every time. Confirm that it's an indeterminate form. Okay, well, dividing by sine over cosine is the same as multiplying by its reciprocal, right? We're going to use that a lot. Okay, and because that makes this really helpful then, because now I have sine in the numerator and sine in the denominator, and both cancel. So now I'm left with 4 cosine pi, 4 cosine x, and I can put pi in right away. I don't have fractional expression anymore. So I can go ahead and put in the pi, cosine of pi, excuse me, if you remember, pi is on the left-hand side of the unit circle, and cosine is the x coordinate. So cosine of pi is -1. -1 times 4 is -4. So the limit, as x approaches pi, of 4 sine x over tan x is -4. Okay, so when we get together as a class, we'll go through the takeaways, and then we'll hit those topic questions, which will be the basis of our more complicated level limits involving the expression. Those are going to be a hoot. All right, we'll see you back in class.